Up to this point, all the concepts that we have discussed are common for both the CPM and the Pert analysis. At this point, we're going to look at Pert particularly, and we'll look at CPM later on. In CPM, we assume that the activity times are fixed and there is no variability in the activity times. But Pert uses probability distribution for activity times to allow for variability. So for example, if we expect a particular activity to take, say, 5 weeks, but we are not certain that it will take 5 weeks. It could be smaller than 5 weeks or it could be more than 5 weeks. Now, is it equally likely between, with 5 at the center, it could be like 1 week earlier or 1 week later with equal probability like in a normal distribution? Well, let's look at it in a different angle. Suppose if we are able to reduce from 5 weeks to a smaller amount, if we are able to finish the activity sooner than 5 weeks. So it could be 4 weeks or 3 weeks. And as you go down, it becomes harder and harder for the activity to be finished earlier than where we were before. So theoretically speaking, even though it is not practical, the smallest you can get is 0. From 5 you can get to 0. You can't go below that. So that's a hard floor for how much smaller the activity time can be. But on the other side, if it gets delayed, the activity gets delayed, so it can go from 5 to 6 weeks or 8 weeks or 10 weeks or 15 weeks or 20 weeks. There is no real hard ceiling for how far off, how much delay there could be in the activity time. So the probability is not symmetric. So it's more like a normal distribution with the upper side tail kind of shifted to the right. Something like this. Yeah. So this is called a beta distribution. So it is reasonable to assume that if the activity times are variable, then it's going to follow something like a beta distribution. So beta distribution has 3 time estimates: optimistic time, that's on the left hand side; pessimistic time, that's on the right hand side; and most likely time, that's in the middle, with the pessimistic time kind of extended further out than A. If this is so, if we assume beta distribution, then the expected time for the activity can be computed using this formula. This comes from beta distribution: A plus 4m plus B over 6. And variance for activities will come from this function. It doesn't include m, but it is B minus A over 6, the whole thing squared, or B minus A squared over 36. Now let's look at an example. So this is the same example, the Milwaukee paper project. So we have activities going from A through H, and let's assume that these are the 3 optimistic, most likely, and pessimistic estimates that we have come up with. Then using this formula, we can compute the expected time, and using this formula, we compute the variance. And notice here that I'm not dividing the 36 into 4, because that increases the number of divisions, increases the amount of computation, and also reduces accuracy. I'll talk more about it in a little bit. Now remember, you shouldn't add all these numbers up, because some of these activities are done in parallel. So if you add the expected time, you'll only get the total work content, not the expected project completion time. And similarly, some of all the variances will not give you the project completion time variance. Project completion time variance is given by the sum of only the critical path activities. So we take the critical path activity variances and sum them. Okay, so now you see we did not divide 36 into each of them, because now we can add the numerators and divide by 36 just one time, and that gives you the variance, and take a square root of that, and we get the standard deviation. Now remember, for this project, the expected project completion time was 15 weeks. So now we have expected completion time of 15 weeks and the standard deviation. Now if the activity times are beta distribution, then the project completion time will follow normal distribution, and if the activity times are statistically independent, then we can compute probabilities using normal distribution. So expected time is the mean, the standard deviation we just found out. So now we can compute probabilities, like what is the probability we can complete the project in 16 weeks. In that case, 16 weeks is the due date minus the expected completion time divided by the standard deviation gives you the z value. Now you take the z value to the normal distribution table in the back of the book. In the appendix, 0.57 gives you the probability. This is the cumulative probability, in other words, the probability that we can complete the project in 16 weeks. If you do 1 minus this, that will give you the probability that we will not be able to complete the project in 15 weeks. Now you can turn this around and then say, all right, probability is given and we want the due date for that probability. Then this is the probability of completion. Now go to the normal distribution table and find z. That z is 2.325. Then the due date is given by this formula. T sub e plus z times sigma sub p. So T sub e is 15. Z, we just looked it up, 2.325, and then substitute sigma there, and that's your sigma, and you get your due date, which is 19.1 weeks. There is one more thing we should keep in mind, that if the second longest path, which is not a critical path, but if the second longest path has a higher variance than the critical path, then the probabilities of the second longest path will be very important. So you have to compute probabilities for the second longest path also. You do that only if the second longest path has a larger variance or larger standard deviation than the critical path.